Hi, welcome all to the online classes. I'm Mukesh Bhardwaj. Today going to represent a topic rectifiers, which is in the BTech Agriculture fourth semester, subject applied electronics and instrumentation. Now, rectifiers rectifiers are basically in large number of electronic circuits we require DC voltage for operation. We can easily convert the AC voltage or AC current into DC voltage or DC current by using a device called PN junction diode. One of the most important application of PN junction diode is rectification of alternating current, AC into direct current DC. A PN junction diode allows electric current in one forward bias only in forward bias condition and blocks electric current in reverse bias condition. In simple words, a diode allows electric current in one direction. This unique property of diode allows it to act like a rectifier. So, basically, a basic component of a diode is a rectifier, or basic component of a rectifier is a diode. So, diode is a basic element which is used in the rectifier circuits, or we can say the rectifiers are basically made up of diodes. And the concept of rectifier is that we require the direct voltage or direct current or DC voltage or DC current instead of wherever we want the DC voltage or DC current instead of alternating voltage or alternating current. So we need to convert the alternating current or alternating voltage because direct current or direct voltage are not available, or they are not you may call it that it is not easily in a continuous way. Either you can get the DC voltage or DC current through the batteries or some sort of energy storage devices. They are providing the direct current, but in a continuous manner. If you want to get a direct current or direct voltage, and that cannot be possible because the direct current source or voltage source are battery sources, and they are relatively costlier or expensive also. So wherever we are just in the continuous need of direct current, we used to design the rectifiers, and rectifiers basically convert alternating current into direct current, and alternating current can be produced very easily through the hydroelectric power plants, through the thermoelectric power plants, and the household supplies which we get are in the alternating form. And wherever the applications which are controlled by the direct or current or direct voltage, we just put an adapter in front of or in continuation to the alternating current, and we get the direct current or direct voltage. So the basic building block or basic element for the rectifying circuits are diode, and we are well aware about the diode circuits, diode types of diodes, configuration of diodes, working of diodes. And in a very short review, I can say that diodes are behave like a valve, or we can say that diodes are behave like a switch, or they allow current in one direction but does not allow the current in other direction. So it's a unidirectional property. Due to its unidirectional property, it is used as a rectifying circuit. So the PN junction diode allows electric current in forward bias condition and blocks electric current in reverse bias condition. In simple words, a PN junction diode allows electric current only in only one direction. This unique property of the diode allows it to act like a rectifier. When AC voltage or AC current is applied across the PN junction diode, during the positive half cycle, the diode is forward biased and allows electric current through it. However, when the alternating current AC current reverses its direction to negative half cycle, that the diode reverse biased and does not allow electric current through it. In simple words, during the positive half cycle, the diode allows current, and during the negative half cycle, the diode blocks current. Thus, electric current flows through the diode only during the positive half cycle of the AC current. This current which flows across the diode is nothing but a DC current. Thus, the PN junction diode acts like a rectifier by converting the AC current into DC current. So basically, the diode acts like a rectifier because it is going to convert the alternating current into direct current. However, the DC current produced by a basic rectifier, half-wave rectifier, is not a pure DC current. It is a pulsating DC current. Suppose if an AC current is just as an input through a PN junction diode, so the only positive half cycles will be passed on through the diodes and the negative half cycles will be clipped off. And this is called pulsating direct current or pulsating DC. And this will not going to solve our purpose because the fluctuation is so or the ripple factor is very high in this case. So we need to get a full or simple or constant direct current instead of pulsating direct current. The pulsating direct current is a type of DC current whose value changes over a short period. The pulsating DC current starts from zero and grows to maximum forward current peak level. And decreases to zero and decreases to zero and decreases to zero. However, the pulsating DC current does not change its direction periodically like alternating current. The pulsating direct current always flows in one direction like the pure DC current. However, the value of pulsating DC current or pulsating DC voltage slightly changes over a given period. The electric current produced by batteries, power supplies, and solar panels is pure DC current. By using the combination of components such as capacitors, inductors, and resistors in the circuit, we can achieve the smoothing of pulsating DC to pure DC. So, this is the smoothing process is done by the filtration, and with rectifiers, we use the filter circuits to get the pure or smooth DC. Now, types of rectifiers. Rectifiers are basically of two types. One is the half-wave rectifier, and second is the full-wave rectifier. Half-wave rectifier, as the name suggests, the half-wave rectifier is a type of rectifier which converts half of the AC input signal, that is positive half cycle, into pulsating DC output signal, and the remaining half signal, negative half cycle, is blocked or lost. In half-wave rectifier circuit, we use only a single diode. Now, full-wave rectifier. The full-wave rectifier is a type of rectifier which converts the full AC input signal or positive half cycle and negative half cycle to pulsating DC output signal. Unlike the half-wave rectifier, the input signal is not wasted in full-wave rectifier. The efficiency of the full wave rectifier is high as compared to the half wave rectifier. AC adapter consists of all the essential components needed to convert AC to DC conversion. For AC to DC conversion. Here AC adapter means for example, while doing the mobile chargers, while doing the mobile charging, or while doing connecting the laptop through the main AC current, a adapter is connected in between the wire, or through the adapter we just get the voltage, and that voltage is the DC voltage. And in the encapsulation of that um, encapsulation of that particular, what we can say, the adapter, there is a circuitry arrangement of diodes, filters, or small transformers, or small voltage step down voltage transformers are there. So these components are transformers, capacitors, and several diodes. Out of these components, the main key component is the diode, which converts the alternating current into direct current. The transformer in the AC adapter reduce the high AC voltage to a low AC voltage, that is step down transformers are used. The rectifier made up of diodes converts this low AC voltage or AC current into low DC voltage or DC current. However, converted current is not pure DC current. It is pulsating DC current. The capacitor filters this pulsating DC current into pure DC. So a filter circuit is associated in continuation with rectifying circuits, which give the pure DC. A half wave rectifier is a type of rectifier which converts the positive half cycle, positive current of the input signal, into pulsating DC direct current output signal. Or a half wave rectifier is a type of rectifier which allows only one half cycle, either positive half cycle or negative half cycle of the AC input AC signal, while the another half cycle is blocked. So this is the diagrammatic representation of a half wave rectifier, where you are just getting the pulsating direct current as an output. Half wave rectifier is the simplest form of the rectifier. We use only a single diode to construct the half wave rectifier. The half wave rectifier is made up of an AC source, transformer, step down diode, and resistor, that is load. The diode is placed between the transformer and the resistor load. So this is the diagrammatic representation of a single or half wave rectifier. AC input signal is just connect to the transformer, and the transformer coils are shown up as the primary windings and the secondary windings. The positive half cycle conducts the diode in a forward, or the biasing is in the forward biasing, and then the diode start conducting, and the output comes in a positive half. But when the direction reverses, or the negative half cycle enters through the transformer, the polarity gets changed, and as the polarity of the second winding gets changed, then the diode comes into the reverse biasing, and it will not allow to conduct a current through it, and therefore it drops to zero, and the result come out to be as a zero till to the next positive half cycle. So this is the diagrammatic representation. Next, AC source. The AC source supplies alternating current to the circuit. The alternating current is often represented by a sinusoidal waveform. Transformer. Transformer is a device which reduce or increase the AC voltage, that is step up or step down. The step down transformer reduces AC voltage from high to low, whereas the step up transformer increases the AC voltage from low to high. In half wave rectifier, we generally use a step down transformer because the voltage needed for the diode is very small. Applying a large AC voltage without using transformer will permanently destroy the diode. So we use a step down transformer in a half wave rectifier. However, in some cases we use a step up transformer. In step down transformer, the primary winding has more turns than the secondary winding. So the step down transformer reduces the voltage from primary winding to the secondary winding. Half wave rectifier operation. When high AC voltage 60 Hz is applied, 220 volts, 60 Hz is applied, the step down transformer reduces the high voltage into low voltage. Thus, a low voltage is produced at the secondary winding of the transformer. The low voltage produced at the secondary winding of the transformer is called secondary voltage. The AC voltage or AC signal applied to the transformer is nothing but an input AC signal or input AC voltage. The low AC voltage produced by the step down transformer is directly applied to the diode. This low AC voltage produced by the step down transformer is directly applied to the diode. So this is the diagrammatic representation. The diode allows electric current during the positive half cycle, forward bias, and blocks electric current during the negative half cycle, that is reverse bias. The positive half rectifier does not the positive half wave rectifier does not completely block the negative half cycle. It allows a small portion negative half cycle or small negative current. Current is produced by the minority carriers in the diode, and the current produced by the minority carrier is very small, so it is neglected. We can't visually see the small portion of negative half cycle at the output. Next, the resistor placed at the output consumes the DC current generated by the diode, and the resistor is also known as the electrical load. The output DC voltage or DC current is measured across the load resistance RL. The electrical load is nothing but an electrical component of a circuit that consumes electric current. In half wave rectifier, the resistor consumes the DC current generated by the diode. So the resistor in half wave rectifier is known as load. Sometimes the load is also refers to the power consumed by the circuit. Thus, the half wave rectifier produces a series of positive sinusoidal pulses or negative sinusoidal pulses. This series of positive pulses or negative pulses is not a pure direct current, it is a pulsating direct current. The pulsating direct current changes its values over a short period of time, but our aim is to produce a direct current which does not change its value over a short period of time. Therefore, the pulsating direct current is not much useful. Half wave rectifier with capacitor filter. A half wave filter converts the pulsating direct current into pure direct current. In half wave rectifier, a capacitor or inductor is used as filter to convert the pulsating DC to pure DC. The output voltage produced by half wave rectifier is not constant. It varies with respect to time. In practical application, a constant DC supply voltage is needed. In order to produce a constant DC voltage, we need to suppress the ripples of the DC or DC voltage. This can be achieved by using either a capacitor filter or inductor filter at the output side. In the below circuit, we are using the capacitor filter. The capacitor filter at the output side smoothen the pulsating DC to pure DC. This is the half wave rectifier with filter capacitor. So, as we are just put a capacitor in parallel to the load resistance, so the output which are getting through the load resistance is less pulsating and it is filtered out through the capacitor. Characteristic of half wave rectifier. Ripple factor. The direct current DC produced by half wave rectifier is not pure DC but a pulsating DC. In the output pulsating DC signal, refined ripples. These ripples in the output DC can be reduced by using filters such as capacitors and inductors. In order to measure how much ripples are there in output DC signal, we use a factor known as ripple factor. The ripple factor is denoted by gamma. The ripple factor tells us the amount of ripples present in the output DC signal. A large ripple factor indicates a high pulsating DC signal, while a low ripple factor indicates a low pulsating DC signal. If the ripple factor is very low, then it indicates that the output DC current is closer to the pure DC current. In simple words, the lower the ripple factor, the smoother the output DC signal. Ripple factor can be mathematically defined as the ratio of RMS value of AC component of the output voltage to the DC component of the output voltage. So the ripple factor is equals to RMS value of AC component of the output voltage to the DC component of the output voltage. So the ripple factor is given as gamma is equals to under root Vrms upon Vdc whole square minus 1. Finally, we get gamma equals to 1.21. The unwanted ripple present in the output along with the DC voltage is 121% of the DC magnitude. This indicates that the half wave rectifier is not an efficient AC to DC converter. The high ripples in the half wave rectifiers can be reduced by using filters. Now, peak withstand. If the applied voltage is greater than the peak inverse voltage, the diode will be destroyed. So the peak inverse voltage is the maximum reverse bias voltage up to which a diode can withstand. Beyond to this limit, the diode will be destroyed. During the positive half cycle, the diode is forward biased and allow electric current. This current is dropped at the registered load RL. However, during the negative half cycle, the diode is reverse biased and does not allow the electric current, so the input AC current or AC voltage is dropped at the diode. The maximum voltage drop at the diode is nothing but an input voltage. Therefore, peak inverse voltage of the diode is equal to Vs maximum. Rectifier efficiency. This is the third parameter. Rectifier efficiency is defined as the ratio of output DC power to the input AC power. The rectifier efficiency of half-wave rectifier is 40.6%. Now the fourth characteristic of fourth parameter, that is root mean square value of load current, that is IRMS. The root mean square value or root mean square value of a load current in a half-wave rectifier is IRMS equals to I maximum by 2. Now the fifth characteristics, that is VRMS. So VRMS or root mean square value of output load voltage VRMS in half-wave rectifier is equals to IRMS into RL equals to Im by 2 into RL. Now the sixth parameter or sixth characteristic is form factor. So the form factor is defined as the ratio of RMS value to the DC value. It can be mathematically written as form factor equals to RMS value upon DC value. The form factor of a half-wave rectifier is 1.57. Advantage of half-wave rectifier. We use very few components to construct the half-wave rectifier. So the cost is very low, easy to construct. Disadvantages of half-wave rectifier. First is power loss. The half-wave rectifier either allows the positive half cycle or negative half cycle. So the remaining half cycle is wasted. Approximately half of the applied voltage is wasted in the half-wave rectifier. Pulsating direct current. The direct current produced by the half-wave rectifier is not pure direct current. It is a pulsating direct current which is not much useful, produce low output voltage. Half-wave rectifier with the filters. When AC voltage is applied during the positive half cycle, the diode D is forward biased and allows the electric current through it. As we already know that capacitor provides a high resistive path to DC component, low frequency signal, and low resistive path to AC component, that is high frequency signal. So electric current always prefers to flow through a low resistance path. So when the electric current reaches the filter, the DC component experiences a high resistance from the capacitor, and AC component experiences a low resistance from the capacitor. The DC component does not like to flow through the capacitor, that is high resistance path. So they find an alternative path, that is low resistance path, and flows to the low resistance RL through that path. This is the pictorial representation of a filter circuit. On the other hand, The AC component experiences a low resistance from the capacitor. So the AC component easily passes through the capacitor. Only a small part of the AC component passes through the load resistor, that is RL, producing a small ripple voltage at the output. The passage of AC components through the capacitor is nothing but charging of the capacitor. In simple words, the AC component is nothing but an excess current that flows through the capacitor and charges it. This prevents any sudden change in the voltage at the output. During the conduction period, the capacitor charges to the maximum value of the supply voltage. When the voltage between the plates of the capacitor is equal to the supply voltage, the capacitor is said to be fully charged. This is the diagrammatic representation in corresponding to the AC input. We are just getting the DC output. Half-wave rectifier with filter output waveforms. As we are observing this, the little bit fluctuations are occur. Okay. So this is called pulsating DC. When the capacitor is fully charged, it holds the charge until the input AC supply to the rectifier reaches the negative half cycle. When the negative half cycle is reached, the diode get reverse bias and stop allowing electric current through it. During this non-conduction period, the input voltage is less than that of capacitor voltage. So the capacitor discharges all the stored charge through the load resistance RL. This prevents the output load voltage from falling to zero. The capacitor discharges until the input supply voltage is less than capacitor voltage. When the input supply voltage is greater than the capacitor voltage, the capacitor again starts charging. When the positive half cycle is reached again, the diode D is forward biased and allows electric current. This makes capacitor to charge again. The capacitor filter with a large discharge time constant will produce a very smooth DC voltage. Thus, a smooth and steady DC voltage is used by using the filter. Now, we are going to start with full wave rectifier. A half wave rectifier uses only a single diode to convert AC to DC. So it is very easy to construct the half wave rectifier. However, a single diode in half wave rectifier only allows either a positive half cycle or a negative half cycle of the input AC signal, and the remaining half cycle of the input AC signal is blocked. As a result, a large amount of power is wasted. Furthermore, the half wave rectifier are not suitable in the applications which need a steady and smooth DC voltage. So the half wave rectifiers are not efficient AC to DC converters. We can easily overcome this drawback by using another type of rectifier known as full wave rectifier. The full wave rectifier has some basic advantages over the half wave rectifier. The average DC output voltage produced by the by the full wave rectifier is higher than half wave rectifier. Furthermore, the DC output signal of the full wave rectifier has fewer ripples than the half wave rectifier. As a result, we get a smoother output DC voltage. A full wave rectifier is a type of rectifier which converts both half cycles of the AC signal into pulsating DC signal. This is the diagrammatically presentation of a full wave rectifier or center tap full wave rectifier, because full wave rectifier is of again two type. One is the center tap and second one is the bridge rectifier. So this is the center tap rectifier. So as you observe in the figure that a line or the load resistance or the load is connected just in the between of the secondary windings or secondary coil, and we are getting the output across this load resistance, and two diodes are connected in the given figure shown, and AC input signal is applied. So as you are observing, the direction of current during positive half cycle is also in from left to right through the load resistance, and for the negative half cycle again the current direction will be from the left to right, right to left side. So the output DC signal is just something which we get like this, that is not it is again pulsating, but we cannot say it is drops to zero for an instant and just start increasing frequently. The full wave rectifier is further classified into two types: center tap full wave rectifier and full wave bridge rectifier. Before going to the working of the center tap full wave rectifier, let us first take a look at the center tap transformer. Because the center tap transformer plays a key role in the center tap full wave rectifier. When an additional wire is connected across the exact middle of the secondary winding of the transformer, it is known as the center tap transformer. The wire is adjusted in such a way that it falls in the exact middle of the secondary winding. So the wire is exactly at the 0 volt of the AC signal. This wire is known as the center tap. The center tap transformer works almost similar to a normal transformer. Like a normal transformer, the center tap transformer also increases or reduces the AC voltage. However, a center tap transformer has another important feature, that is the secondary winding of the center tap transformer divides inputs AC current or AC signal into two parts. The center tap full wave rectifier is made up of an AC source, a center tap transformer, two diodes, and a load resistance. So this is the diagrammatic representation of a center tap transformer and the center tap rectifier, full wave rectifier. The AC source is connected. Wait a minute. The AC source is connected The AC source is connected to the primary winding of the center tap transformer. A center tap additional wire connected to the exact middle of the secondary winding divides the input voltage into two parts. The upper part of the secondary winding is connected to the diode D1 and the lower part of the secondary winding is connected to the diode D2. Both diode D1 and D2 are connected to a common load RL with the help of center tap transformer. The center tap is generally considered as the ground point or the zero voltage reference point. During the positive half cycle of the input AC signal, a terminal A becomes positive, terminal B becomes negative. And center tap is ground. 0 volt. The positive terminal A is connected to the P side of the diode D1 and the diode negative terminal B is connected uh, and the negative terminal B is connected to the N side of the diode D1. So the diode D1 is forward biased during the positive half cycle and allows electric current through it. During the positive half cycle, current flows only in the upper part of the circuit, while the lower part of the circuit carry no current to the load resistance or to the load. Because the diode D2 is reverse biased, during the positive half cycle of the input AC signal, only diode D1 allows electric current, while diode D2 does not allow electric current. During the negative half cycle of the input AC signal, a terminal A become negative, terminal B become positive, and center tap is grounded 0 volt. The negative A is connected to the P side of the diode D1 and the positive terminal B is connected to the N side of the diode D1. So the diode D1 is reverse biased during the negative half cycle and does not allow electric current through it. So this is the diagrammatic representation for the negative half cycle. Diode D2 is start conducting and diode D1 gets off and the current start flowing through the load resistance in the same direction as flow through the D1. As a result, both half cycle, positive and negative of the input AC signal are allowed. So the output DC voltage is almost equal to the input AC voltage. Now this is the complete diagrammatic representation of a center tap full wave rectifier. Now output waveform of a full wave rectifier. As AC input signal, in respect to AC input signal, D1 for the positive half cycle and D2 are the for the negative half cycle, and the output total will get in the pulsating DC instead of alternating current. Now characteristics of the full wave rectifier. As we had discussed the characteristics in half wave rectifier, similarly the characteristics need to be discussed for the full wave rectifier. The ripple factor is used to measure the amount of ripples present in the output DC signal. A high ripple factor indicates high pulsating DC signal, while low ripple factor indicates low pulsating DC signal. Ripple factor is defined as the ratio of ripple voltage to the pure DC voltage. The ripple factor is given by gamma equals to root Vrms upon Vdc upon whole square minus 1. And finally, we get ripple equals to 0.48. Rectifier efficiency. Rectifier efficiency indicates how efficiently the rectifier converts AC into DC. A high percentage of rectifier efficiency indicates a good rectifier, while a low percentage of rectifier efficiency indicates an inefficient rectifier. Rectifier efficiency is defined as the ratio of DC output voltage or DC output power to the AC input power. It can be mathematically written as rectifier efficiency neta is equals to output upon input. The rectifier efficiency of full wave rectifier is 81.2%. The rectifier of a full wave rectifier is twice that of half wave rectifier. So the full wave rectifier is more efficient than a half wave rectifier. Peak inverse voltage. Peak inverse voltage or peak reverse voltage is the maximum voltage a diode can withstand in the reverse bias condition. If the applied voltage is greater than peak inverse voltage, the diode will permanently destroy, as in the same case as in the half wave rectifier. The peak inverse voltage is equals to 2V S max. DC output current, the fourth parameter, at the output load resistance RL, both the diode D1 and diode D2 currents flow in the same direction. So the output current is the sum of D1 and D2 currents. The output produced by D1 is I max by pi, and the current produced by the D2 is I max by pi. So the output current IDC equals to 2I max upon pi, where I max equals to the maximum DC load current. So that is all for today's lecture, and we will continue the remaining parameters and the advantages and disadvantages, and the center tap full wave rectifier with filters. After that, uh, after that bridge rectifier, very important rectifier, and having very high efficiency. And then advantage and disadvantage of bridge rectifier. And after that, we are just moving some questionnaires and quiz related to the rectifier circuits. And this is all about for today's lecture. Thank you. Thanks a lot. Have a nice day.